This is actually a really good opportunity for us to use a cool feature of Vim to explore system headers. So if we go ahead and open a new C file and we include the header where these definitions are located, if we put our cursor over the header file name here and we type GD for go to definition, Vim will actually take us to that header file where it's located. And then from here, we can kind of see what we're looking for isn't actually in this header, but there's a comment that tips us off here that they're actually located here. So GD, and then it turns out that they're located in this include, and here we go. Here's all the things we're looking for. So that's a nice way to quickly follow headers around, and it can't always be very useful for system headers because of these transitive includes that happen. You can end up really chasing things around for a while. But if we go back to our test file and we just place one of these macros here, if we use GD on this macro, Vim will actually take us directly to where that was defined. So that's a really nice feature. It allows us to kind of explore these sorts of things. And you can use this in your program as well if you want to go back to where a variable was declared or a function definition. You can do that very quickly and easily. Now, if you're not using Vim, there are other ways to do this. So for example, one way is to leverage the preprocessor. Preprocessor doesn't allow you to redefine a macro that's already been defined without first undefining it. So a nice little trick is you could define this macro, which we know is already defined somewhere else, and then we can make this file, we can compile it, and we get a warning, and it tells us exactly where that macro was originally defined, what file it was defined in, and it shows us sort of backtrace of the inclusion steps that got us there. So it's this header file, and then this header file, and then this one. So we could copy this path and go to line 43, and there is the original definition. So those are just a couple of ways to explore things like that, and this can come in handy a lot when you're working on a really large project that is large enough to have its own internal header files, and you want to find where something was defined. So if we go back to this file, we can actually see what these values are. So these are written in octal. If you're not familiar with it, each digit represents 3 bits and can have a value 0 through 7. In binary, this is 1, 0, right? This is 0, 1, and this is 0, 0. Then we see this access mode mask here, which is 1, 1. So where you would use this is, let's say you had a flag value. If you AND it with access mode, it's going to give you those lower 2 bits. So it's going to clear all of the other bits in that flags value and just give you these lower 2 bits. And then you can compare it to see if it's O read only or something along those lines. Here we see the create exclusive and no CTTY, no controlling terminal flags are all 6 zeros, 6 trailing zeros in binary, and then 1, 1, 0, and 1, 0, 0. Okay, so again, these don't overlap at all with any of the other flags, and they just set one particular bit in that value. And then this continues with these 3 macros, truncate, append, and non-blocking IO are all particular bits with 9 trailing zeros. So 1, 1, 0, 1, 0, 0 with 9 trailing zeros. And then this sync macro here is a little different. It actually has 2 bits set, so it's a 1, 0 with 3 zeros, and then a 1, and so this is 0, 0, 1. So it's 1, 0, 0, 0, 0, 0, 0, 0, 1, and then 12 zeros. Then we have async, which is 1, 0, and then 12 trailing zeros. And so on and so forth. We have some extra internal implementation features here, and some other flags for other things for file control, and so on and so forth. When you're constructing the flags, you're ORing together different individual bits of this integer value. And this is actually really common in system interfaces to use flags like this, because in C, every argument to a function is passed in a particular register or on the stack. Passing each of these as an individual argument would require a lot of registers and stack space, and it would make the function really slow. So cramming everything into a single flags argument is pretty handy. And so this is commonly used in system interfaces. And now why an integer? Well, it's because that was sort of back in the day when C was first devised. All character data for text was a char. And all integers were ints, and that was basically it. So int is frequently used just because that was sort of the default data type back then, and it's large enough for most purposes like this, especially because on a modern system an integer is 32 bits instead of 16, so that gives you quite a few different flags that you can set. If C were being completely redesigned from scratch, I'm fairly certain we would switch to fixed width integer types, like the uint 8, 16, 32, and 64, and these system calls would instead use those types for their flags instead, to be very explicit. But it's just kind of a quirk of history here.